want to thank Eric and Elation for putting this all together. It's really important to keep up with the technology today. I wrote this book called Automated Lighting, The Art and Science of Moving Light in 2003. It was published by Focal Press. And then I revised it in 2010. And from 2003 to 2010, hardly any changes at all. It was really easy to update it. But then they asked me to revise it again. So I started rewriting it around last November, December. And I took a look at all the changes from 2010 to 2015. Mind-blowing. You know, there's new technology in power supplies. Of course, the big thing is LEDs. So almost everything is LED now. There's still a lot of arc lamp technology out there, but it's getting better and better all the time. And of course, now we have network stuff. We have software that's just, what the software engineers say is that software is eating the world. By that, what they mean by that is that hardware, like big consoles. Remember, when I first got into this industry in the 1800s, the bigger your console was, the more important you were. Now, lighting programmers just want to be able to carry a console, put it in the overhead bin, bring it to a gig, program in their hotel room, program in the office or from home, and then bring the thumb drive in and transfer it over. That's what's most important. And so now we have all these software platforms that are just incredible. We have, we have visualizers, and we have offline editors and things that emulate consoles with all the right buttons, and we have touch screens, and we have, what I have is I run a offline editor with a touch screen and a 4K television for my second monitor, a UHD TV, so I can split it into 4 screens, and each one of those 4 panes is a full HD 1080 display. So you can have very fine print and you can read it. So the technology has really, really grown a lot, exponentially over the last 5 years, and it's going to continue to do that. So it's vitally important to re-educate yourself. There's experience is good, and looking at all of you guys, I'm guessing that a lot of you have some really great experience, and that's good. But experience doesn't always teach you the right lessons. I'll tell you what I mean. A few years ago, I was working on a show, a Dierks Bentley show. There were 4 follow spots. I went and pulled the follow spots, to prep the gear before the show. And they were all Super Troopers that have an external ballast. And so I went and got the follow spots, and I went and got the power supply. And I pulled the first power supply, and the cable on it, the power cable, had the green grounding conductor was external. It wasn't inside of the cable, it was outside of it. And where it went to the connector, the wire was broken. And I thought, oh, that's unfortunate. So I went and got another one. Same thing. The green grounding wire was broken off. And so was the third, and so was the fourth. And it wasn't as if these things had just broken the day before or the week before or even the month before. I mean, because the wires were all frayed and they were oxidized, it looked like it had been that way for years. And so the takeaway for somebody who used those follow spots with those power supplies, they'll do a show that at the end of the night show's over, they shut down the follow spot, they pack it up, put it on the truck, and they look at the green grounding wire and go, I didn't need that. It must be superfluous. It must just be there for cosmetic reasons. It's just to make it look pretty. Wrong. That can kill you. So it's really important to understand how to recognize hazards, because that's a potentially lethal hazard. The first time there's a short to the case of the follow spot and somebody's touching the follow spot, the metal part, the metal chassis of the follow spot, and a scaffold at the same time, they become the path for fault current, and it could kill you. And people have gotten hurt and injured that way a lot. So the first thing we're going to talk about is how to protect yourself and how to recognize these hazards. Some real basic things about electricity. But even before we do that, here's what I want to do. I'd like for you, all of you, to think about why you're here, and I'd like for you to write down very concisely, say a little mission statement for the class. By the end of the day today, what do you want to know? Where do you want to be? Are there particular questions you want answered? And so that way I think you'll get more out of the class. There's a guy named Dr. Stephen Covey who wrote a book called 7 Habits of Highly Effective People. Has anybody ever read that book before? It's a really good book. I recommend that you read it. He basically studied people who he considered to be what he called successful, which I would call, he said effective. I would call them successful. And he recognized these common traits in them. And one of those common traits was that highly effective people always begin with an end in mind. What does that mean? Well, just like you'd never jump in your car and start driving before you knew where you're going, you should never start any endeavor without first knowing where it is that you want to be at the end of the trip. So think about your purpose for being here. And the more you can crystallize that and put it in writing, the more effectively you'll be able to reach that goal. So if you have particular questions in mind, I'd like for you to write those down, okay? So this is a very important part of this class. If at any point there's something you don't understand, please feel free to raise your hand, stop me and ask a question. I'll be happy to address your questions. And that also gives me feedback to make sure that I'm reaching you and that we're on the right track for what you want. So, is that okay? Can everybody agree to that? All right, good deal. My name is Richard Cadena, and my background is in electrical engineering. I studied electrical engineering at the University of Texas, but I didn't want to go to work for Dell or IBM because I didn't want to make too much money, so I got in the lighting industry. And I went to work for this company called Blackstone Audio Visual. And after I was there for a year, they changed their name to High-End Systems. And I worked there for 13 years. And then since then, I've been freelancing, writing books, writing magazine articles. These are the 4 books that I've written. The 2 most popular are the Electricity for Entertainment Electricians and Technicians, and then the Automated Lighting book. Focus on Lighting is a bit dated. Don't buy that book. And then Lighting Design for Modern Houses of Worship is a book that I wrote based on my experience doing church lighting design and that kind of stuff. I currently write magazine columns for Lighting and Sound America and Lighting and Sound International and Protocol magazines. Those are all free subscriptions. Besides my articles, there's some really good stuff in there. So everything in there is really good except for the stuff I write. So, and then I am an ETCP certified entertainment electrician, which means I took the electrician exam and passed it. I'm also a recognized trainer, which means that if you are certified already, then this counts as recertification points. Is anybody here certified? No? Okay. Something you might think about doing, maybe long term, Last November, down in Argentina, there was a guy named... Sorry?
My people.
Is that right? You're from Argentina? So do you know the band, the Krebs? Are you familiar with the Krebs?
Actually, no.
Okay, they're kind of a new band. They were up and coming, and on November 27th, 2014, the lead singer was electrocuted doing a sound check. His only crime was he had his guitar and he grabbed the microphone. It killed him. Why did that happen? And it's not the first time that this has happened. If you look back through history, you'll see that it's happened over and over and over again. This guy, Les Harvey, was the lead singer for a band called Stone the Crows. And he got electrocuted live on stage before a live audience. And then Keith Relf from the Yardbirds. Have you heard this little band called Led Zeppelin? Well, before they were Led Zeppelin, they were called the Yardbirds. And Keith was the lead singer, and he got electrocuted in his home studio recording because of faulty grounding. This guy, Chad Gilbert, of a band called Newfound Glory, he almost died in 2013. Same thing. He's got a vintage amplifier. He's holding the guitar strings. He grabbed the microphone, and he started getting shocked. And sometimes what happens is your muscle seize and you can't let go. They freeze. And that's what happened to him. He couldn't let go, and he fell to the ground. And luckily, the impact jarred the microphone loose, and that probably saved his life, because if he hadn't been able to let go, then he would have been killed. And then just in 2014, actually that should be 2015. This guy, and I don't know who this singer is, Norberto from Alcala. Well, here, I'll just show it to you. There's a, see if I can get this video to start. So he's singing, he's performing, and then he touches a scaffold, and he's getting shocked. He falls to the ground. He's completely unconscious, and luckily they were able to revive him. A few minutes later, he went back on stage and finished the show, which that amazes me. You know, if it would have been me, I would have gone to the hospital and gotten checked out, because you never know. Sometimes you get shocked. You might think you're okay. You walk away and you might have internal injuries, and it could be a major serious problems later on. So why do these things happen? You know, a few years ago, I did a lot of research into this kind of thing. And are you guys familiar with OSHA, the Occupational Safety and Health Act? And they have a website. Well, their job is to keep you safe on the job, to make sure that you have safe working conditions. And anytime there's an accident, they come out and they investigate, and then they issue a report and they post it online. So you can go to OSHA.gov and you can look at the accident reports. And so if you do that, there's a search box. And if you try this, you go to the website, and in the search box, type in electrocution, just to see what comes up. Now, what is electrocution? You know, the definition of electrocution is death by electricity, right? It's kind of funny that when Chad Gilbert got shocked, the headlines on the internet the next day said, Chad Gilbert survives electrocution. Well, you don't survive an electrocution, because by definition, it's death by electricity. Fortunately, he survived. But if you go to the OSHA website and you type in electrocution, you'll see all the reports about people who have been electrocuted on the job. And unfortunately, there's a lot of them. But what I did is I looked at them to try to figure out what causes these things. And in general, what happens is that there's two main causes of electrocution. And this is very unscientific. This is just my own observation from looking at them. But about half of the electrocutions occur from overhead power lines. So if you're doing shows outside, you have to be especially vigilant about overhead power lines. Stay away from them, at least 30 feet. And that's because a lot of times, you know, we have scaffold, or we have ladders, or we have something that extends our reach, like a grip pole, or, you know, piece of conduit, or piece of truss. So at least 30 feet away is a good rule of thumb. And it's easy to forget that there's power lines there. You get into what you're doing and you forget about it, and that's trouble. You know, there have been people that have been electrocuted because they're erecting tent poles, and you stand the pole up and it goes right into power line, and it kills some people in the Carolinas doing that. There were 2 film students from NYU that had just graduated from college, and they went down to Atlanta to shoot a film, and they were in a bucket, a personnel lift, and they went right into the power lines, killed one of them. So that's the kind of thing that when you have an argument with the power line, you're going to lose every time. So you really need to be careful about power lines. The other half of the electrocutions tend to occur because of faulty grounding. What does that mean? Well, remember the broken green wire on the follow spots I was telling you about? That's an example of a faulty ground. So when you're setting up your power distribution, you know, part of your job is to inspect all the cables. Make sure they're not broken. Make sure that the insulation is not cut or frayed or abrased or cracked, or, you know, make sure it's in good condition. You know, that rubber insulation only lasts a certain amount of time before it starts deteriorating and breaking down. And you know, if you do outdoor shows, the UV sun rays will crack that insulation. Okay? So part of your job is to inspect the gear as you're setting it up. Make sure there's no broken pins, broken connectors, broken wires, that kind of stuff. That's really important. So what is it about electricity that can kill you? Is it the voltage or the current? Does anybody know? Is it voltage or current that will kill you? Current. It's the current. And how much current does it take to kill you? Not much. And I'll show you a chart in a moment. But these are the things that determine how badly you'll be injured if you get shocked. And by the way, how many people here have never been shocked before? How many people have been shocked? Right. See, it happens. And so we have to take steps to protect yourself because it's going to happen. One of the first gigs I ever had in the lighting industry, I was wiring in some lights on a truss in a nightclub, and I was at the top of a ladder, and I was going to reposition myself, and I grabbed another piece of truss that had 120 volts on it. And I grabbed it. Luckily, I was able to let go. That's number one. Number two, I was lucky enough not to fall 16 feet down to the ground on top of the ladder. Somebody was looking out for me. But it happens. So how do you protect yourself? That's part of what we're going to talk about. You wear gloves at certain times. You wear rubber-soled shoes. These shoes right here are EH rated, meaning electrical hazard rated. And they're built to insulate you from the earth so that in the event that you do get shocked, it won't be as severe. So that's an example of a way you can protect yourself. I wear these things everywhere. And so when I'm out on a job and I happen to get called to go do a tie-in or whatever, I'm around, perfect example. Last February, I was working the NBA All-Star Weekend in Brooklyn, and I had to go out to the production trailer, the TV trailer. And on the way out there, you go out in the yards. Anybody ever been to an event like that that's being broadcast? And there's tons of generators, there's tons of production, there's the TV trucks. In this case, there was probably 5 or 6 TV trucks. Cables going everywhere. We're talking about 4/0 feeder cable, big giant feeder cable, strewn all over the ground, and it was snowing, so the ground was wet. It was muddy and wet. There were puddles of water. And here I am walking across, and there's no way to avoid stepping on those cables. So I felt a little bit more secure in that I was wearing, and I have another pair of Reeboks that are EH rated. They're more like boots. And so I felt a little bit more secure stepping on them. I still, scurried across as fast as I could, because you can't help but step on the cable. But under those conditions, it can be hazardous. And there have been instances. There was a guy out in Central Park. They were doing a show out in Central Park. He stepped on a feeder cable. It put him in the hospital because the jacket on the feeder was broken. So when you step on it, it's like stepping on a live conductor. He stepped on a live conductor. So that's why it's good to have this type of protection. But if you do get shocked, how badly you're injured depends on the amount of current that flows through your body. It depends on the length of time that current flows. If you're shocked for a longer period of time, that's worse than if it's just a brief shock. And then also the size of the person, because that determines the resistance of your body, which that determines how much current will flow through it, and then the path that current takes through your body. So if current goes through your vital organs, your heart, your brains, your lungs, your liver, that's worse than if it doesn't go through vital organs. So now, how much current does it take to harm you? Well, this is a chart that shows the effect of current. This is alternating current at 60 hertz, which is what we use in North America. And everything in the green is safe. But over here in the yellow and in the red, that's potentially lethal. So what this is telling you is, and this is the amount of current going this way. So here's 1 amp. So starting at about, this is 200, 300, no, that's not right, 100, 200, somewhere around 300 or 400 milliamps is where it starts getting really dangerous. But even if you're down here at 10 milliamps for more than 2 seconds, about 3 seconds, 10 milliamps. Now, how many milliamps are in 1 amp? 1,000. So a milliamp is 1/1000th of an amp. It's not very much. So if you're shocked with 10 of those for 3 seconds, That puts you in the yellow zone, which says, this is AC3, it says muscle contraction, so your muscle seize. And if your muscle seize and you can't let go, then you're going to be shocked for a longer period of time, which makes it even more dangerous. So when you start getting into, around 30, 40 milliamps, that's when you can start getting into the red, which is probability of heart fibrillation, meaning your heart starts beating irregularly, and that's potentially lethal. So it doesn't take a whole lot of current to cause serious problems, possibly even death. So what is it that determines how much current will flow through your body? Well, it depends on the voltage and the resistance. So this is Ohm's law. It tells you the current flowing through your body depends on the voltage you're shocked with and the resistance of your body. And who here knows how much resistance is in the human body? Anybody have any idea? Well, I found some information about that. So this comes from a book about electrical safety, and it shows you the resistance based on whether your skin is dry or wet. Notice that if your skin is wet, that the resistance is a lot lower. If you have lower resistance, then what that means is that the current will be higher. So when your skin is wet, when it's raining, when you're standing in a puddle of water, when your shoes are wet, your resistance drops. And so that makes any voltage a lot more dangerous. So the wet skin resistance and dry skin resistance. And then basically, the bigger the surface area of contact, the lower the resistance, the higher the current will be. So for example, finger touch, just one finger touch, the resistance is pretty high. It can be as high as 1 million ohms. That's a lot, So that's why everybody here that raised their hand when I said, who here has been shocked before? That's why we're still here. Because the resistance was high enough that the current was low enough that we survived it. But had the circumstances been something else, then you and I might not be here. So that's a really important thing. Now think about this. If you're touching guitar strings, and the guitar strings connect to the bridge, and when you plug in the guitar cable, the bridge connects to the shield of that cable. The shield of the cable goes to the guitar amplifier, and the amplifier is plugged into the wall. So the strings are grounded. They're connected to electrical ground. And then when you touch the guitar strings, you have a lot of surface contact. And then when you grab a microphone, again, a lot of skin surface is contacting the metal chassis of the microphone. And again, the microphone is connected to the cable with the shield. The shield's plugged into the PA. The shield is connected to the chassis of the PA. The chassis of the PA is connected to that green grounding conductor. So you've got the green grounding conductor from the PA, green grounding conductor from your amplifier. And if there's a short, meaning that a hot wire, one of the black wires the insulation breaks and leans up against the chassis, now the chassis has voltage on it, but it has nowhere to go in certain instances if there's a faulty ground. If the ground is intact, it will immediately cause the circuit breaker to trip. But if the green wire is broken, or if it's not there because the audio engineer lifted the ground, have you ever seen those ground lift adapters? You know what I'm talking about? When you get a ground loop, you take a 3-prong connector from the amplifier, you plug it into the adapter, so now it has 2 prongs. What's that third prong? It's the green grounding conductor. And if it's not connected, if there's a fault, now the amplifier is at line voltage, is at 120 volts. It's got nowhere to go until somebody touches the guitar strings and then touches the microphone. And now you've connected the circuit through your heart. And that's how people die. So it's really important to never, ever, ever, under any circumstances, lift the ground. Or if you recognize there's a faulty ground, if the green wire's broken, fix it. Don't use that piece of gear. It's potentially lethal. And when Chad Gilbert got shocked and almost lost his life, He went to the hospital and got checked out, and they released him the next day. When that happened, I went online and started doing research trying to figure out what happened, just like I do every time there's an accident like that. And if you go into the audio forums, and there's a lot of these online forums, then a lot of the techs were talking about how common this problem is. These backline techs get shocked all the time because of faulty ground. And so it's way more common than we might know. So knowing that, let's look at, so I compare this situation right here to 2 hands around a 1.5 inch pipe. It's probably about the same surface area contact. So I would guess the resistance of the body would be about the same, which is to say it's between 500 ohms and 1500 ohms, depending on how hard you press, exactly how much skin is contacting, all those conditions. So if we take that middle value, say for example, it's 1,000 ohms, okay? And if it's 1,000 ohms, and we said that, say for example, if you get frozen on, if your muscle seize and you can't let go, then 10 milliamps, or let's say 30 milliamps. 30 milliamps could potentially kill you. So if we look back at this equation right here, let's plug in 30 milliamps, and that's 0.03 amps. So I'm going to write this down. So the current is the voltage divided by the resistance, or another way of saying this is V equals I times R. If I is 0.03 and R is 1,000, how many volts is that? How many volts is that? What's 0.03 times 1,000? Get your calculator out if you have trouble with decimals. It's 30 volts. So what this says, all this discussion we've just been saying is that 30 volts is potentially lethal. Now, how many people here believe that 30 volts could possibly kill you under the wrong circumstances? Yeah? There's the math. It actually could. It actually could. And if you really want your mind blown, go online and Google 32 volt electrocution. Because you know what? It just so happens that I was doing some research trying to figure out, I was trying to find the lowest voltage that somebody had been killed by. Lo and behold, there are some workers in China who were working inside of a tank. They were welding a big giant tank, steel tank. It was hot. They were sweaty, which means that their skin resistance was low. They were wet. The resistance in their body was low, and they were also dehydrated, which also affects your internal resistance. And they got electrocuted by 32 volts. Not one person, more than one person. 32 volts. If you go on those online audio forums, there are people on the online forum saying 120 volts, that can't kill you. Really? I beg to differ. It actually can kill you. And 120 volts has killed way too many people. So the point of all this is don't ever let your guard down. The most important thing is to understand what affects the severity of the situation. What affects how badly I'll be injured if I get shocked? And the answer is Ohm's law. So if the current is high enough, then that's a potential problem. Now we have no control over the voltage. If you get shocked, you can't say, oh, time out, let me go change the voltage. You can't do that. The voltage is the voltage. What you do have control over is the resistance. How much resistance will you present to that load? When I got shocked wiring those lights, had I been wearing gloves, then the resistance would have been a lot higher, even if they were cotton gloves. Now, cotton's not the best insulator in the world. The best insulator in terms of gloves is rubber. And you can buy voltage rated gloves. I have a pair. They're rated up to 1,000 volts. And they cost about $85 for the rubber gloves, for the leather covers, because you don't want the rubber to get nicked or cut, so you put leather over the top of them. It protects them. It also comes with a canvas bag, so that when you're finished, you put them in a canvas bag, throw them in your toolbox, and a screwdriver won't puncture the rubber. It protects them. 85 bucks, that's a pretty good investment. I'm not saying you wear those everywhere you go when you're on a gig, but certain times, if you ever have to do, has anybody here ever had to do a live tie-in? You know, where you take your feeder cable and you have to connect it without the benefit of a switch. You should have that switch, but not all venues have a switch. So in that instance, then you put on those rubber gloves with the leather covers, and you'll be a lot more safe. And you can also make sure you're not standing on a bare concrete floor, because believe it or not, concrete is a pretty good conductor. So you want to insulate yourself from the floor. You want to stand on a piece of carpet, or what I like to do is carry around a rubber yoga mat. And so if I have to do something like that, I'll take the yoga mat, fold it over, throw it down on the ground, stand on top of it while I'm wearing my electrical hazard rated shoes, finish my work, and then the bonus is once I'm finished, I can just do my yoga right there, and I'm good for the day. So think about that. But yeah, so with 30 milliamps, if the resistance of your skin is 1,000 ohms, which is not terribly unreasonable, then 30 volts is potentially lethal. So, keep your guard up. Always respect electricity. Now, I would love to see us use more GFCIs. How many people here know what a GFCI is? Ground fault circuit interrupter. Okay, that's good. About a third to a half. Okay, so for those of you who don't know, it's those outlets in your bathroom with the red and black button. Those have protection on them. And the idea is that if somebody's being shocked, it detects what's called leakage current, because when you're being shocked, current's going through your body, it's leaking out of the circuit that it's supposed to be in. And when it detects a tiny bit of leakage, which is 6 milliamps or more, then it will shut itself off. And they will save your life. Those GFCIs are designed to save 99% of the world's population from lethal shock. So who's the 1% that it won't save? Well, very, very small infants and very elderly, or people with health problems. But everybody else, if you're a healthy adult, then a GFCI will save your life. Now, keep in mind, they have electronic components in them, and those, it's got integrated circuit chips, it's got transistors, and all these parts inside. Any one of those can fail at any time, and there's no outward indication. So don't purposely rely on that to save your life, but you put it in as a backup, as a safeguard. And that's also why it has the red and black button, to test to make sure all the electronics are working. If you press the black button, you should hear it click off. That means that the electronics are working. And then you press the red button to reset it, and it's ready to go. And you should test them every 30 days. And if you look at, around 1970 is when we started using GFCIs. And over the years, we've used more and more and more of them. So this is the number of GFCIs in millions. So if you look at around 2000 or beyond, there's about 30 million of these in use. And if you look at the number of household electrocutions, they have steadily fallen in inverse proportion to the number of GFCIs that we've been using. What does that tell you? It should tell you that these things save lives and that we should be using them. There's a standard for the use of GFCIs in the entertainment industry. And basically what it says is that anytime you use electricity in the proximity of water or moisture, you should be on GFCI protection. If there's a possibility that it could rain, and I know it will rain in Southern California because I was here in December and it was raining. I didn't believe it until then, but I saw it with my own eyes. So even though it seldom rains in California, you still need to be on GFCI protection. if there's a possibility it could rain, if there's a possibility of dew on the ground, if there's a possibility of a sprinkler system coming on, and you're outdoors. And personally, I think we should be using GFCIs for all of our backline gear. That means amplifiers, keyboards, PA system. Well, maybe not big giant PA, because it's very expensive, and it's sometimes hard to get PA to work with GFCIs, because audio systems generate what are called harmonics, and those have trouble working with GFCIs. But you should at least try it. Try to get it on GFCI, because that will totally eliminate all those electrocutions like Augustine Briolini last November, and Keith Relf, and Stone the Crows, and all those, that would totally be eliminated. Everywhere else in the world, in Europe, Australia, they use something that is similar to a GFCI called an RCD, a residual current device, or an earth leakage circuit breaker, ELCB. And they have to have them on all their outlets. So anytime you go to a stage and plug in, you're protected. That's the way it should be. Now, there's no laws or codes that says you have to do that in North America, but there's no laws or codes that say you can't do that in North America. And these things come in a variety of form factors. There are portable GFCIs like this that you can buy for about $10 or $15. And this is a 20 amp circuit. So it would be great if we had a whole bunch of these that we could start to use. Balmore, you had your hand up first.
How long do they last?
Yeah, they'll last a long time.
Yeah.
Actually,
can it take like damage, like drop them?
Yeah, they're pretty durable. Yes,
Durable?
Yeah, they'll last years. Now there is a study they did recently, and they're finding out that of all, we said there's 30 million GFCIs that were in use by the year 2000. It turns out that about 3/4 of those are no longer functioning. So you do have to test them. They won't last forever, and you have to replace them if they don't work. So, every night before I go to bed, I'm brushing my teeth, I'm playing with the red and black buttons on my GFCIs in my bathroom. Every time I go to a hotel room, I test the GFCI in there, because you never know, it could save somebody's life. So get in the habit of every time you see GFCI, as long as it's something that you can shut off power to, go ahead and test it out. Or if you work for a production company, you have rental gear and you have GFCIs, every time they come back from a gig, they should be tested. And every time they go out for a gig, before they go, they should be tested. Okay? Justin? Jacob, sorry.
Is a lever strip or a surge protector, does that offer similar protection?
No. There is surge protection, and there's also uninterruptible power supplies, UPS. And some UPSs have surge protection in them. And a UPS you'll see at front of house a lot because it has a backup battery. And depending on how big the UPS is, if you lose power, it'll keep the console going for 15 or 20 minutes, which is enough time for you to back up your console and save your show before you lose power, in case power takes more than a few minutes to come back on. Those do not have GFCI protection on them. And honestly, it may be difficult to take a UPS and plug it into a GFCI, because a UPS, the way it draws current, is not in a sine wave, which is the normal way to do it. It's usually in pulses, which means that a GFCI reads that as leakage current, and it will probably trip. So my recommendation would be try it out. See if you can get it to work with a GFCI, portable GFCI. And if you can't, then here's what you do. There's 5 ways we protect ourselves from electricity. Those 5 ways are insulation. That's why wires are covered with rubber or with plastic. There's isolation, which is why transmission towers are generally way out in the country, or if they're not in the country, they're on very, very high towers, so it's very difficult to get tangled up in the cables. And those cables, by the way, generally don't have insulation, so they're isolated. There's circuit breakers. there's grounding, and there's GFCIs. So the best way to protect people from electrocution, in my opinion, is to use GFCI protection. If you can't get it to work on GFCI protection, now I hear this a lot from audio engineers. I've tried and I've tried and I've tried. I can't get this amplifier or this whatever to work with GFCI. Okay, well if that's the case, how about isolating it? Put it behind an audience or crowd barrier. Put it backstage. Elevate it. Get it up out of the way where not even the talent can touch it. You know, I was working a show one time where the production company sent out power distribution racks, and they have the cam connectors, and it had cam throughs, which means that if you want to connect from one power distribution box to another, it has connectors for that. So you just run a cable from that one to the next one. They're plastic covers. So the cam connectors have these plastic covers, spring-loaded covers that fold down on it so that there will be no live exposed copper. But those break, right? And in this particular situation, the pass-throughs, the covers were broken off, so there was, you could see copper. There was live exposed conductors. So if somebody, you know, for whatever reason, came in contact with it, if they leaned against it, they could accidentally get shocked. And that's a lot of current. It would be bad. It would be really bad. So since the cam covers were broken off, I built a barrier around it with chairs so that nobody could even get to it. I tried to isolate it. So if you think about those 5 ways that we protect ourselves, you'll be a lot safer. And so will your whole crew, so will the talent, so will everybody that comes in contact with that stuff. Does that answer your question, Jacob?
Yeah.
Okay. So check these out. You know, a friend of mine lives out in, I think it's Woodland Hills, somewhere LA area, is a guitar player. And he has a 1962 vintage Fender Blackface amplifier. And it's very, very valuable, right? After this incident happened last November, I was in contact with him and I said, hey, you know, your amplifier probably has a 2-prong connector because it's vintage. You know, back in the 60s, in the early 60s, they didn't use grounding. Everything was 2-wire. There's a black wire, there's a white wire. There was no green wire. That's just the way they built electrical systems back then. But over the years, they learned how important the grounding systems are. So today, it's vitally important that, or it's highly regulated that when you build an electrical system, it has a grounding system. Or otherwise, it will not pass code. But back then, they didn't. So his amplifier has a 2-prong connector on it. And so I contacted him and I said, next time I'm in California, I'm coming by, I'm going to replace your power cable and put a 3-prong connector on it. He said, over my dead body you will. I'm like, what? This thing's vintage. It's worth $40,000. If you alter it in any way, it'll cut the value in half. I'm like, oh, that's a problem. So you know what I did? I sent him one of these. I said, here, just put this in your guitar case or whatever, and whenever you go to a gig, just plug that in, plug your amplifier into it, plug it in. Now, if there's a fault to the chassis when you touch your guitar strings, it'll shut off power. And again, this is an audio device, so I'm not sure how well it's going to work, and I've asked them for feedback. Let me know how it works, and I haven't heard from. You know, I've been asking them periodically. Is everything okay? Does it work? Is everything, you know? So far, so good. So hopefully, fingers crossed, it stays that way. Okay. Does that make sense?
Yeah.
Okay. Good deal. So yeah, you know, vintage amplifiers. If you look at, if anybody here works with backline gear, take a look at the equipment. Make sure that it's properly grounded. If it's not, it really needs to be on GFCI protection. And that, you know, my buddy Jim is my guinea pig, and as far as I know, it seems to work. So here's another thing you can do. You know, I have this contact voltage detector. So if you know, a lot of shows I work, I have no control over the back line or even designing the electrical system. I might just be a hired hand. So what I'm going to do is, anytime I'm on the stage, I carry a voltage detector in my pocket, usually in my back pocket or my side pocket, and I'll pull it out. All you have to do is touch something with it. And it looks like this, and this is a plastic tip. And when you touch it to something that's hot, it glows red, turns on. So you can touch the microphone, you can touch the chassis of the amplifier. Anything made of metal can potentially have voltage on it. And if it has voltage and somebody touches it, they're completing a path to earth, they can get shocked. So you'll see me on shows walking around with my voltage detector, touching the truss, touching the amplifier chassis, touching the microphones, touching even the stage, the bracing for the stage, to make sure there's no stray voltage. There's no it's actually called contact voltage on that piece of metal.
What happens if you find voltage? How will you start to troubleshoot it?
Well, it depends on the situation. If you find voltage, say on the microphone, then the first thing I'm going to do is I'm going to, you follow the chain of command, but you get the power shut off to that piece of gear first, and then you track down the problem. If it's, say it's a microphone, then chances are it's a faulty ground. You've got to go to the amplifier that's powering that device and look at the ground. The next thing I'll do is I'll take my ohm meter and I check for continuity between the chassis of the amplifier and any grounded piece of metal, the building steel, piece of truss, to see if there's continuity. If there's not, that means you either have a broken green grounding conductor or a pin on the connector, or somebody purposely lifted the ground. And there's a point at which things are too dangerous. In our industry we have this philosophy. We have a culture really of the show must go on. Well, yeah, it must go on as long as it can go on safely. So part of your job is to be able to figure out what is safe and what is unsafe. You've got to be able to recognize hazards. That's a potentially lethal hazard. That's what I would call imminent danger. And imminent danger is defined by OSHA and by a couple of other places, NFPA 70E, for example, as a situation that could potentially cause death or physical harm immediately or before it can be remedied. And if you think there's imminent danger, it's your right and it's your responsibility to put the brakes on and figure out what the problem is and fix it however you can, because you don't want somebody to get hurt. So that's the whole idea. Is let's protect ourselves and the people around us. Yeah. Sorry, what's your name?
Jason.
Jason. Okay.
Is the ground lift on like a DI? Is that safe?
Okay. Now there's a difference between. So the question is, there's a ground lift on a direct box, what's called a DI, direct interface. So if you take, say for example, they use these a lot on bass guitars because they don't want to mic the bass amplifier. So they'll take the bass signal and run it through the PA. It sounds better. And to do that, you need to adjust the line level of the signal from the bass. So they'll take this box that changes the signal level to input into the PA system so it sounds right. So it's essentially a cable that's going through this box, and then there's a switch on it, and the switch says if you flip the switch, you're breaking the ground connection. There's a difference between a safety ground and a signal ground. When you break the connection on the shield of the cable, that's the signal ground, and that's what causes ground loops, which sounds like that hum through the PA system. That's perfectly okay. What you don't want to do under any circumstances is break the safety ground, which is the green power connector conductor. That's the one you don't want to break. So it's okay to use the ground lift on a DI box or on the back of amplifiers. Sometimes they'll have a switch to break the signal ground. And what it does is when you plug the cable into the amplifier, the shield is connected to the chassis of the amplifier. And if the shield is connected and the safety ground is both connected, now you've got a closed loop and current can flow, and that's what causes that noise. So to break that loop, you flip the switch and that breaks the signal ground, not the safety ground. So the safety ground should never be broken. The signal ground is okay. And you know what? We're going to talk about that later on this afternoon. We've got pictures with arrows and circles and all that kind of stuff. Okay? So, All right. Tell you what, we're going to start talking about electrical circuits real quickly. But before we do that, why don't we go ahead and take a 10-minute break.